Alright, OFDM stands for Orthogonal Frequency Division Multiplexing, and the idea behind this is to combine modulation and multiplexing into one idea. So the good thing with that is, the analogy they use is, instead of having a faucet with just one constant stream of water coming out, you have a kind of like a shower head with multiple streams of water coming out. So if something were to happen, like you would plug your finger over the hole, you wouldn't lose all of your data, you would just lose one little stream of water. Another analogy they use is, instead of one giant truck, they use a bunch of little trucks in order to transport the data. So if there's an accident on the freeway, you wouldn't lose all your data at once. Now this idea works if it's, well, the individual trucks will be called subcarriers, and they have to be orthogonal for that to work, because if they're not orthogonal, then they can interfere with each other. Now, what they do to make the subcarriers orthogonal is they multiply the sine or cosine by just an integer each time. So you have, you have like 1 hertz and 2 hertz and 3 hertz, and those would all be orthogonal just by the definition of a sine and cosine wave. Important thing that OFDM strives to take care of is the idea of fading. Fading is the loss of signal from the transmitter to the receiver as it goes from one place to the other. So it'll go either straight to the receiver or bounce off a building or a tree or whatever. And the good part about OFDM is, if you happen to lose a signal, if the signal fades too much, you lose just 1 over n bits instead of losing the entire signal, and that can usually be recovered by the receiver. On to CDMA, or code division multiple access. To start this, you see that they have a binary signal with a symbol rate of 2, and they modulate it with a sinusoid, and you get this spectrum. Now, if you were to modulate it with another binary signal with bitrate 8 times the previous one, you can get this here spectrum, and that spectrum is now spread from 2 hertz to 16 hertz, or a factor of 8, and that is the spreading factor. Aside from spreading the signal spectrum, this modulating with the binary sequence also introduces a kind of encryption, because you need the same sequence at the receiver to demodulate the signal. And they do this 3 times. The first time with a code called the Walsh code, then with what they call a short code, and then with what they call a long code. Long code is a 2 to the 42 bits sequence that takes 41 days to repeat, and the main purpose of it is to both spread and encrypt the signal. And since those are the 2 things we're trying to accomplish, long code is pretty important. Now, the short code used for synchronization, it repeats every 26.666 milliseconds, and that equates to 75 times every 2 seconds. So it's a lot shorter than a long code. So each base station is assigned one of these codes, but since short code is only one sequence, what they do is they shift the code by what they call a PN offset, like kind of like a phase shift. For example, they use, if they use the word please as a short code, they can shift the P around to the E, and you get this word, and then you can do it again to get this word, and so you can have the same code but shifted. This code they mention here under short code is the Walsh codes, and these creation of multiple channels. So 64 Walsh code could, or 64 Walsh codes could create 64 channels. And the Walsh codes are orthogonal to each other. Alright, and lastly, we're talking about multiple input, multiple output. This is important because the tutorial starts off with single input, single output, and the Claude-Shannon's capacity. We did the example in class, making this table, that you could increase your signal-to-noise ratio by a factor of 10,000, but your bits per hertz would only go up by 13. And doing this it shows that it would take so much power to actually get to actually increase your capacity that it's a little ridiculous trying to do it that way. MIMO it allows, in this graph, it allows you to just increase your number of antennas, and you can increase the channel capacity as bits per hertz. So this is good, because before, with single input, single output, we would need a lot of power to increase our capacity. There's kind of a new Shannon's limit when you're talking about multiple input, multiple output, and this is another new rule, and it allows for you to get a much higher bits per hertz when you increase the number of antennas, as opposed to just increasing power enormously. Another good part about MIMO is diversity. Diversity being how, if you travel through different paths, as we talked about fading back when we talked about OFDM, if one pathway happens to cut out, you still have multiple inputs and multiple outputs. So it says if one path is weak, then a copy of it is received on another path, and that path could be just fine. So you still get your data. To do this, so you need to know a little bit about each channel, and that is made up by a matrix, and these numbers are kind of like the gain of each path. So it'd be like from transmitter 1 to receiver 1, transmitter 1 to receiver 2, and so on like that. So so for 3 receivers and 3 transmitters, there's a total of 9 different paths that can go across.